in this session we shall be dealing with the third chapter of the book Bootstrap Methods with Application in R. Specifically, the chapter deals with the different types of confidence intervals in context to Bootstrap. So, we shall be taking our data called the Surimi data, we would introduce that data, and using that data we shall be calculating the percentile confidence interval, the percentile T confidence interval and the bias corrected confidence interval in context to the Bootstrap technique. The objective here is to explore various different kinds of confidence interval with respect to Bootstrap sampling. So, we would be constructing the different kinds of confidence interval. For example, the percentile confidence interval and the percentile T confidence interval and the bias corrected variants of confidence interval in context to Bootstrap. The reference here would be again the third chapter of Bootstrap Methods with Application to R by Michael R. Charnick and Robert A. Labure, and we would be using their data and the codes there, and we would reproduce those codes, but see line by line that what is done for calculating all these different types of confidence intervals. So, the data is called the Surimi data, and Surimi is purified fish protein used as a material to make imitation crab and shrimp food products. The strength of Surimi gel is a critical factor in production. Each incoming lot of Surimi raw material is sampled and a cooked gel is prepared. From these gels, test proteins are selected and tested for strength. Our sample data are the measured ultimate stresses to penetrate the test portions for 40 incoming lots of Surimi. So, we have, that means we have our data of length 40. So, we have 40 numerical values which reflects the stress to penetrate test portions for 40 lots of Surimi, and the data is given in the book. So, the data looks like these are the 40 values starting with 41.28 to 42.16. So, we can say x and then we can store the data in x, and if we go by summary x, then the value is 29, minimum value is 29.12, maximum is 50.52, variance comes out to be 17.297, standard deviation comes out to be 4.159, and to test normality. So, if the data can be assumed to be normal, we can use Shapiro.test x. So, the Shapiro test for normality or the Shapiro-Wilks normality test, and the p value is nearly significant. So, 0.07. Now, if we assume normality, then what is the confidence interval? So, we define n is length x. So, mean x plus qt 0.975 n minus 1 into SDX. So, that is the factor, and we multiply it by plus 1 and minus 1. So, it is mean x minus qt 0.975 n minus 1 SDX and mean x plus qt 0.975 n minus 1 SDX divided by square root of n. So, that is the student's t base 95% confidence interval which we generally do, and the value comes out to be 40.85 to 43.51. Now, again we can use our non-parametric method and use the percentile technique for calculating the confidence interval. So, here what we would be doing is we would be first creating our non-parametric bootstrap sample, and then we would be obtaining the mean of each of them and see the percentile. So, we start with, again for reproducibility, set.sid, and the value can be different. U naught mean x, that is the mean of the original samples, and then we produce the standard error denoted by SH here, SDX by square root of n, and a vector to store the bootstrap means which is at theta, and then for I runs from 1 to 1000 we start the non-parametric bootstrap resampling. So, we keep the sample in XX, which is sample x n replace true. So, again the sampling is done with replacement, find the mean and store the mean in the ith place for theta, or the ith observation for theta. Then to see what is the mean, bootstrap mean and the original mean, just say u naught and mean thetas, and to print it together we concatenate it into a single vector, and that comes out to be 42.1857 and 42.18038. So, both of them are very similar, and the fact being that the data is more or less normal, and we have 40 observations. So, we get more or less similar means from the original as well as from the bootstrap. Now, quantiles theta probability equal to 0.025 and 0.975, that is the F1 percentile CI, and that comes out to be 40.87 and 43.44, and this is in contrast to 40.85 and 43.51. So, note that the bootstrap non-parametric confidence intervals, the bootstrap percentile confidence interval, the bootstrap being non-parametric bootstrap, results in a confidence interval which is slightly more slightly tighter than the student T based 95% confidence interval. Now, the bootstrap percentile T confidence interval. So, here what we do, we follow the same step, but we also compute the pivotal quantity. So, we define say the standard error and then thetas, but also define T star which stores the pivotal quantity, and for a context to the mean it is u, that is bootstrap estimate minus the true mean divided by standard error of the bootstrap estimate, which is SD of the bootstrap estimate divided by square root of n. So, for each of the bootstrap estimate bootstrap samples, we calculate the mean and we calculate the pivotal quantity. Now, just to compare, again means are very similar. Now, if we compare the standard error from the data and from the original sample and the standard error of the bootstrap, we find that the standard error of the bootstrap is smaller than the standard error computed from the sample, and then we can use quantile T star probabilities equal to 0.025 to 0.975 to obtain the quantiles from bootstrap percentile T, and the quantiles come out to be minus 1.945 to 0.0547. While if we use the same for QT, which is used from, so which are quantiles from students T distribution, that comes out to be minus 2.02 and 2.022. So, to get the lower and the upper confidence intervals, or to get the lower and the upper bootstrap percentile T confidence interval, we can use u naught plus quantile T star probability equal to C 0.025, 0.975 into the standard error, and that comes out to be 40.90 and 43.53. Now, just to compare the student T confidence interval, we use u naught plus QT C 0. So, that means at 0.025 and 0.975 n minus 1 into that the T has n minus 1 degrees of freedom into the standard error, and that comes out to be 40.85, 43.51. Now, we come to bias corrected bootstrap. So, for the bias corrected bootstrap, we define a function called f boot. Now, f boot computes the estimate given data x and index set I. Now, boot theta. So, what does f boot does? F boot is function xi, mean of xi. Now, what is boot theta? Boot theta is a new function that we are creating, and boot theta takes the argument x, n boot theta. So, we would be telling exactly what they are. The idea of this boot theta function is to perform bootstrap resampling to get array of theta star values. So, that means we start with defining, or rather we start with the length of x, so and store it in n, and then create a matrix which has n boot sets of size n. So, if n boot is the number of bootstrap repetitions, so n boot here is number of bootstrap repetitions, then what Bootstrap does is it stores, obviously in a matrix format, the sample x size n into n boot, replace equal to true, n row equal to n boot. So, for each, so it samples n into n boot number of random sample from x and then stores it in a matrix having the number of rows equal to n boot. So, the number of columns is n, and if theta is our function, then we compute theta star, which is apply Bootstrap. So, on the stored matrix of bootstrapped samples, we apply the function theta. So, theta would be a function which would be given by the user, and then return theta star. Now, we define the bias corrected accelerated bootstrap confidence interval. Note that when acceleration is equal to 0, when the acceleration value is set to be 0, then we get the normal bootstrap bias corrected bootstrap confidence interval. So, CI/BCA is the function, which is function acceleration theta hat theta star alpha, and then acceleration is the acceleration constant, theta hat is estimate from original samples, theta star is the bootstrap estimate, and alpha is the confidence interval probabilities. Then we define n boot would be the length of theta star, which is equal to the number of rows of bootstrap, and z naught is q norm sum theta star less than theta hat by n boot. So, then quantile for the bias is what is calculated, the bias quantiles, and the quantile for CI is given by q norm alpha, which has been specified. Then P is P norm z naught plus ZCI by 1 minus acceleration into z naught plus ZCI. So, this is the probability for bias corrected accelerated bias corrected adjustments. Then we can index the quantile using the trunc command, so which converts it into numerics. So, truncates P into n boot, and then CIP is quantile theta star probabilities equal to P, and CI is sort theta star IND, and then we return a list of all the objects which are required. So, if we use this command and say to generate the resample estimates, we use theta star, which is boot theta x n boot equal to 1000 and f boot. So, f boot performs the mean. So, that means theta star is nothing but 1000 bootstrap means, and then if we use CI/BCA, that is our bias corrected acceleration confidence interval formula, and put acceleration equal to 0, that means we are only going for the bias corrected for mean x theta star C 0.025.975. So, that is the probability at which we want, we get the bias corrected confidence interval via acceleration set at 0. And again the estimates we get is 40.9 43.82 and 43.37275. So, the percentile confidence interval that we get here is 40.82, 40.83 and 43.37 rounded to 2 decimal places, whereas the corrected bias corrected we get here is 40.833 and 43.373. So, from 2.5 to 97.5%, it changes to 2.21 to 97.19%. In today's session, we have learned how to perform different types of Bootstrap confidence interval computation in R. In the next session, we would be learning some more practical applications of Bootstrap. So, we would be seeing how we can apply Bootstrap in context to analysis of variance problem.